All right, welcome back to Unit B, Chemistry and the Environment. And this is Chapter 1 still on acid deposition. And in this lesson 1.4, we're going to be looking at measuring and monitoring acid deposition. So mostly we're going to be taking a look at titrations and how we can use this data to figure out the concentration of a strong acid or a strong base. So this might be something chemists might do, environmental chemists might do to figure out what the pH of a lake is, or what the buffering capacity of that lake might be. All right, so let's just dig right into this. So you've got your textbook readings down here. There are a lot of extra examples than what I'm going to be giving you today in this lesson. So make sure you go through some of those extra examples in your textbook after you've watched the video. So first off, let's just define those two terms, qualitative and quantitative. If it had been a while since you've seen those two terms. Qualitative, I always think of quality when I see that word. So qualitative is like the quality of the substance. So it's the characteristics. So we're talking properties, characteristics, or attributes, right? So maybe it can dissolve in water or the color, that kind of thing. Whereas quantitative, we're always dealing with quantities, a numerical value or a measurement. So how long something is, how heavy something is, something's concentration. So those are all numbers. So today we're going to be focusing more on quantitative data. So titrations let us figure out the unknown concentration of a solution by measuring the quantities of another solution that is known to react with it until the endpoint is reached. And in our titrations, we're just going to be dealing with acids and bases. So when we are adding an acid and a base together, we know that a neutralization reaction occurs, right? When you have equal number of base to acid molecules, then you have neutralization. So we use that information to help us figure out the concentrations. We also use something called an indicator, which we have learned about before, indicators, to show us when we've hit that endpoint, basically to show us when neutralization occurs, right? That's our endpoint. When the base and the acid molecules are equal to each other, we have neutralization, and we want to choose an indicator that is going to change at that pH. So what pH would that be? Well, neutralization is a pH of 7. So we want to find it and use indicators that are going to change at a pH of 7. Now, when we're doing a titration, we use some very specialized equipment. Unfortunately, being that we're online, we're not going to be able to use this equipment, but we're going to do some virtual labs as much as possible here. So this is one of the pieces of equipment that we're going to be looking at. This is the burette. This is a very long piece of glassware that contains one of the solutions. And then the other solution that we're going to be dealing with will be down at the bottom. And this is our sample solution. The solution in the burette, we usually know the concentration of this, right? Whereas the sample down below, we don't know. It's our unknown that we're trying to figure out the concentration for. Depending on what this is where our indicator would also go. So depending if it's an acid or a base, we'll start an indicator down here, and then that indicator is going to change color as we add the opposite acid or base to here, and when it's neutral, it should change color, and then we know we've added equal amounts. So we're going to go step by step again, what a titration is, but let's just look at a few different terms. So a titration generally involves carefully adding a measured amount of a known solution called a titrant or a standard solution. And that will be up here in the burette. Okay, so our known is in the burette. And then we're going to add that known solution with known concentration to the sample, which is down below in the Erlenmeyer flask. That's the type of flask, okay? And that's called our sample. So some terms that you want to know, titrant and sample. Titrant on top, sample down below. So these are the steps, the basic steps. First, the sample sample, so remember this is the unknown. So it's not raining. Unknown is carefully measured into an Erlenmeyer flask. So using a pipette. So this example is a pipette with a pipette bulb. So this pipette has measurements on it so that you can get an accurate amount. Like maybe it's 10 milliliters or 25 milliliters of a sample. So it's almost like a thermometer, but it's hollow and it sucks the liquid up it like a straw. And that's what you use the bulb for. You squeeze the bulb out and then you slowly release it to suck up the liquid up the pipette till the level that indicates, like 25 milliliters, whatever it is. Once you've got your pipette full, then you would empty it, as it's showing here, into your, they're calling it a conical flask. We refer to this as an Erlenmeyer. I know my spelling's going to be terrible on that one. Erlenmeyer flask. Then we need to, step B, add a few drops of the indicator, whatever indicator we're using. Typically it's bromothiamyl blue or phenolphthalein, and they're added into the sample. So our indicator, just a few drops in here, it'll change color probably, or it might stay clear. Phenolphthalein will be clear until it hits the endpoint. All right, so after we've added our indicator, then the titrant is poured into a burette with a closed stopcock. Okay, so this is our burette. It's really quite long. It usually can hold up to about 50 milliliters of liquid. And there's, again, graduations all along, so you can see where 1, 2, 3, 4, 5.3 milliliters is. Down below here, this is the stopcock that's being referred to. This is a knob on here that you're going to turn open or closed. All right. You want it to be closed when you're filling it up with your titrant, right? This is your known concentration. So whatever, we know this concentration. This is our titrant. All right, then once you're all set up, you slowly add drops of the titrant by opening the stopcock until you see the pH indicator color change. So you're slowly going to let drips go down here as you turn this knob. You're going to let the drips go in until all of a sudden you see the color change. And that tells you you're at a pH of 7 and that the acid that has been added to the base or vice versa are equal. Right? So acid equals base at this point. Or hydroxide ion for the base is equal to hydronium ions for the acid. Equal. All right, this is the endpoint. Then you stop adding titrant as soon as you hit that endpoint. So this video shows this actually happening. You need to watch this video so you can see this in real life and what this looks like. Okay. There's also a calculation at the end of this video, so another sample calculation that you can use. The only thing is we're going to use the C as our in our formula, and they use M in their formula, but it's exactly the same. Okay, so make sure you take a look at that video. All right, now, because the mole to mole ratio is 1, so when the titrant is neutralized, there's an equal amount of acid to base, right? That's how we know we're at the pH 7. The endpoint, the color changes in our indicator, so we know we've hit the endpoint because our pH is now 7. So we can use this special formula in Science30 to calculate our unknown value. Now, if you have taken Chem 30, this is only going to work, or if you're going to take Chem 30, this formula that we're using is only going to work in Science 30. Okay. In Chemistry 30, you get much more complicated because you're going to actually use acids that could donate 2 or 3 hydrogen ions, and that kind of messes things up. So, but for purposes of Science 30, we are going to assume that the moles of the acid are equal to the moles of the base when we're at the endpoint, neutralized. Okay, and because of this, it lets us use this formula. I'm just going to show you how this formula works. So this is the actual formula here. This is on page page 10 of your data booklet. Okay, so make sure you see that on there, circle it so you know that's the one you're going to be using. Why does this work? Why? Okay, so let's take a look. So let's look at the number of moles of acid. Now, this is going to take you back to Science 10. Don't worry if you don't remember too much. We're not going to use this a whole lot. But the number of moles of acid is equal to, like, N represents moles, right? And that's going to be equal to the concentration times the volume. All right. So when you are, that'll tell you the moles of the acid. All right. Now, if you want to know moles of base, same formula, concentration times the volume of the base. Now, we know at the end point, right? At the end point, the moles of the base have to be have to equal the moles of the acid, right? So moles of acid equals moles of base. So if you sub in your CFVF, that's the moles. That's going to equal the moles of base, right? There's the moles of base. And we know that has to equal the moles of the acid at the end point. So there's our formula for moles of acid. Boom. So our moles of acid have to equal the moles of the base at the end point. At end point. It's really important. It has to be at the end point. And that's why we can use this formula. All right. So let's try using this formula, shall we? Okay, so here's an example question. I know there's a lot of writing on here, so I'll walk you through this. Before we even do the calculation, there's a few things you need to understand about these titrations and the data. Now, if you haven't yet, I would stop this, pause this, go and watch that video of what a titration looks like in real life. So go back a couple slides in the slide deck and watch that video, and then come back here. Okay. All right, so an example calculation. So we have a 0.150 mole per liter solution. So there's a concentration of a sodium hydroxide. Okay, is that an acid or a base? Well, as soon as you see OH, you better be thinking base. Okay, so there's our base. They're are titrated into 10 milliliter samples. Okay, so our sample is of an unknown concentration of hydrochloric acid. Okay, so this is our acid. And our sample is our acid. Okay, and there's a volume. Using the data below, determine the concentration of the hydrochloric acid. Alrighty, so few little things here first off. Now, there's not a lot of drawing space on here. What I'm going to do is quickly draw. There's my Erlenmeyer flask where my sample is. Here's my burette where my titrant is. Okay, this is where the known solution is going to be. The one that you know the concentration of. So I know the concentration of this base, right? It tells us the concentration is 0.150 solution of sodium hydroxide. So the sodium hydroxide is in my burette. And the acid sample of unknown 10 milliliters is down below here in my sample. Just so we understand where everything is. Alrighty. So in this titration, you're going to be adding the base, sodium hydroxide, into the sample. So when you start, let's look here. First off, this first question is, why is there initial and final burette readings? Yeah, why does it do that? Final, initial. Okay, so when you start a titration experiment, you need to, before you start adding the amount of volume from this burette into your sample, you need to figure out where you're starting at. So in this case, I'm going to do this in another color. Red's a good color for this one. So we took a reading and the initial burette volume is 0.2. Okay, that's where it's at. So it's almost full up to the top. 0.2 is full, yes. 50 is total, but the numbers go backwards. Okay, there's 50 mils in here total, but the numbers go backwards. So down at the bottom would be like 50. So what you need to do is you need to figure out how much you're going to add. So you take your initial reading and you write it down. All right, then you slowly open the stopcock here and you let the liquid go through, drip, 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 until all of a sudden the color changes. Ooh, yellow. Ooh, we might have gone too far. So it turns us to yellow. We stop it and we read where the level of the liquid is in the burette. And the final burette reading is 13.3. All right, now this is the amount that you've added because it's gone now. Right? The levels have gone down as you added the liquid into the sample down below. So you need to figure out how much liquid you actually added. So what you do is you take your final, the bigger number, subtract the smaller number, and there is the actual volume. So that difference is the 13.1. That's the volume of the base that was actually added to the sample in that trial. Now, how much was in the sample? Every single time, there's 10 mils down below of the sample. All right, so they do one trial and they get the yellow color change. Well, then they do it again and they know roughly where it's going to be, how much volume it's going to take from this burette. So in the second sample, second trial, let's get another color here. They are going to start again. Instead of refilling up this burette, they know they have enough to do another trial, so they're going to take the initial reading. The initial reading, you notice, is 13.3 because that's where it ended. So our initial burette reading is 13.3. We have a new sample down below. We got rid of the old one, washed it all out, got a new sample, and then we start adding or letting it drip, drip, drip down. So the liquid slowly goes down and then stops when it turns orange down below, the color change. And it stopped at 26.0. So that's our new reading, 26.0. So how do we figure out how much we added? We're going to subtract 13.3 from 26 and we get 12.7. So 12.7 is the volume that was added to make the sample change colors. Okay, you keep repeating this. Now you'll notice that 3 of these trials turned orange and 1 was yellow. This is because as we did more trials, we knew more closer idea of how much volume it was going to take to change the color to our endpoint. So these trials got better and better. So what we do typically is you'll see there's usually 4 trials and you get rid of the one that has like the weirdest off number basically. So like if you look at these numbers, 12.7, 12.8, 12.8 volumes were added and 13.1. This one's a bit off. So we're going to get rid of that and we're going to use these trials to give us our average volume of sodium hydroxide added. And yes, we're going to take the average in a second. Alrighty. So that answers the why there's 4 trials, because it can be tricky, and why the numbers are different in every trial. But you'll notice the actual volume added in each trial is very similar, right? Okay. So on to the next page. Let's try and do this calculation now. So step 1, list the information given in the question and convert everything into liters. Find the average volume of titrant added. So I explained why we are getting rid of this trial already. These are our 3 trials. Let's find the average of those trials. And remember, for average, you're just going to add them all together and divide by 3. So 12.7 plus 12.8 plus 12.8 and divide them all by 3. And that equals 12.8. Well, 12.7666, but we're going to round it. We need to only have 3 significant digits, so 12.8 will work. So, and this is in milliliters. How do I know that? It says that right there. So let's change that to liters because that's something we need to work with. We're going to try and work in liters. So remember, to change to liters, you need to divide by 1,000. So that gives us 0.0128 liters. So this is the volume of sodium hydroxide. So that's the volume. Sodium hydroxide is our base, right? So I'm going to use B for the base. Alrighty, let's see what else we have. We had this 0.150 moles per liter. That's the concentration of the sodium hydroxide, which is our base. So we have our concentration of our base. We know that each time we use a 10 mils of sample of our unknown hydrochloric acid. This is our acid, so this is the volume of the acid. I'll use an A for that. Volume of the acid. Now let's change that to liters as well, because that's in milliliters. So let's change that to liters. Again, divide by 1,000. And that gives 0.1 liters. All right, so that's the volume of our acid. All right, so now we have 3 pieces of data, and we're going to try and use this formula down below here. I'm going to rewrite the formula up over here, just so I have a little bit more space. And I'm also going to rewrite it so I use A's and B's for acids and base. It's the same formula, but instead of initial and final, I'm going to use C, the concentration of the acid, times the volume of the acid, because you want to make sure the acid data is all on one side, and then the concentration of the base and the volume of the base is on the other side. Now, when you don't see a plus or a negative sign here, that's multiplication. Okay, so you're going to multiply the concentration of the acid times the volume of the acid, concentration of the base times the volume of the base. Now, what are we trying to find? Now, let's pop them all in here. So concentration of the acid, that's our unknown. We don't know it yet. That's what we're trying to find, so I'm going to leave it there. Then I'm going to multiply by the volume of the acid. The volume of the acid is our sample, so it is the 0.1 liters. And that's equal to the concentration of our base, which was given 0.150 moles per liter, times the volume of our base, which we found down below here is the average volume that we added from our titrant, 28 liters. Alrighty, so a little bit of math reworking here. So you're going to divide both sides by 0.1 liters so that we can get that out of there and bring it over here. So you could have rearranged this formula ahead of time if you wanted. I just didn't, but you can. So our concentration of the acid is going to be the 0.15 times 0.0127, then divide by 0.1. Pause and try that on your calculator. Right, and my answer is 0.0192. And what am I trying to find? Concentration has units of moles per liter. And all of our significant digits, let's just see. We had 3 significant digits in that number. There's 4 significant digits there, and we had 3 in our average here. So we should have 3 in our answer, and that is what we have. So leading zeros don't count as significant. It's just the numbers that follow do. So that's 3 significant digits, so we are good. So that is our final answer. That's the concentration of the acid. So we're going to end it there. Remember to go back and watch the other example in the video if you haven't already, and go through the next few pages. There's a few more examples that are written out for you that you might want to take a peek at and just make sure you understand the steps of the titration calculation.